Today we're talking about exponentials and logarithms, but I'm going to explain something that goes beyond 99% of the knowledge of people who has already finished high school. And truthfully speaking, it is so important indeed that it makes exponentials and logarithms something that simply cannot be avoided in the world of math. Let us dive into it together. So the structure of today's lesson is quite clear. We're going to first learn the definition. Then after that, we'll learn about the identities of exponentials and logarithms alike. I am assuming that you have already learned about basic exponential functions. We won't be going too deep into the identities of exponential functions, but we will prove the identities for logarithms. Let us begin. The graph you're seeing is the exponential function, and let's just first move the slider around and see what's happening. So it is essentially a curve, and you might notice that throughout the entire process, y never became less than 0. So a special point is when a equals 1, and when a equals 1, this thing degrades into a constant function where y is always equal to 1. When a is greater than 1, it is going to bend upwards towards the positive direction, whereas if it is less than 1, then it is going to bend upwards towards the negative direction. However, a can never become a value less than 0. The reason is quite clear. For instance, suppose the function a to the xth power. In this case, suppose a is equal to negative 1. When x is equal to 1, a to the xth power is equal to negative 1. While if x is equal to 2, a to the xth power is 1. So this thing is actually vibrating between 1 and negative 1, and it is extremely hard to describe exactly what is going on because exponentials, they are just a genuinely crazy thing. So in this case, we're just studying a greater than 0. And I'm assuming that you are aware of operations of exponentials like a to the x to the yth power is a to the x to the yth power with the parentheses above. And also, suppose it is below, then this is simply a to the x times yth power. And also, we have the property a to the x power times a to the yth power is equal to a to the x plus yth power. Finally, a to the 1 over x power is equal to the xth root of a. Now, perhaps after learning exponentials, you might have at some point asked the question, suppose a to the x power is equal to b. Then what is x? Can we solve for this? It doesn't really works. However, suppose we apply some function. This answer can't be answered by what we already know. So it is natural we define something. We define log base a of b is equal to x in this case. And essentially we have solved it because we are just defining it. We don't know how to solve it using existing math, so we defined it. And then when we look at this, we're going to see some very interesting properties. And generally, textbooks, they give different sequences in explaining these properties. However, I do think there is a nice rule that I will explain first, which is called the power rule. Essentially, what we're doing is that we want to study the first rule that I'm going to give, which in my opinion is the most important, is the product to sum identity. And this means that we can simplify log base a of x times y to some extent. How then can we simplify this? We know by definition this a to the log a base a of x times y is equal to x times y. And we also know a to the log base a of x is equal to x, and a to the log base a of y is equal to y. So if we multiply these two terms, we get a to the log a of x plus log base a of y is equal to xy. So these two equations are in fact the same. This means log base a of x times y is equal to log base a of x plus log base a of y. This is a very useful identity. And then after that, we can also prove something useful, which is what I call the power rule, where essentially I'm trying to apply the product to sum rule of log a of x to the kth power. We can assume k is an integer, then in that case, k times log this is equal to k times log a of x, which makes a lot of sense. So that is why I'm explaining the product to sum rule first. But this is not complete because sometimes k is not an integer. How do we deal with it then by definition? We know log a of x to the kth power. It essentially means a to the log a of x to the kth power is equal to x to the kth power. And then we also know a to the log a of x is equal to x. So a to the log a of x kth degree is equal to x to the kth degree. And we have already known that this expression over here is a to the k times log a of x. Again, we have proven the same identity here. Now, let us move on to a really interesting thing that at first I did not think is possible, because this is very counterintuitive when you think about the definition of logarithms. For these first two identities, I think it's natural to say that when we have products or powers, there might be a close simplification. However, in this case, there is not. It is not directly related with multiplication. Essentially, we are starting from the definition a to the x degree is equal to b. Then imagine if you apply a logarithm of some base. We'll just leave this empty to represent some base. So a quick note on terminology. We'll write LG as log 10. We'll write ln, the natural logarithm, as log e. E is a constant we'll get into very soon. And then finally, at the moment, just treat e as any other base. And apart from that, everything else is assumed to be written clearly. So log base of b must be written log b. When there is nothing here, then that means we're just saying that any base, except of course b equals 1, will work. And of course the base also must be greater than 0. So imagine applying log to each side. This turns into x times log a is equal to log b. Then x is equal to log b divided by log a. And you might have discovered that we somehow obtained a new expression, because previously we defined x to be log a of b. That means log b over log a is simply log a of b. That is a really interesting conclusion. So this identity over here is called the change of base formula. And it essentially means that whenever you write a logarithm like this, you can move the base downwards, move the target variable upwards, and write it as a fraction. Apply any logarithm to these two values, and it is still true. Now, after we have learned the change of base formula, let's go back to this identity, because we only mentioned when something changes in the parentheses over here. What about if we change the base? Assuming the base is log a to the k1th power, and the number being applied to the logarithm is x to the k2th power. Then that means this expression is equal to log a to the k1th power under log x to the k2th power, which is equal to k2 over k1 times log a of x. In this version, we have proven that, in fact, we can move the base, the exponent of the base, out as well. This is the better power rule. That is all you need to know about logarithms. And since we have been doing all this talk, let's take a look at logarithmic graphs. We will be drawing this by hand, so we can get a better understanding of what is going on. First, assume we're drawing log base a of x, and a is greater than 1. First of all, suppose x is equal to 1. Then log a of x must be equal to 0, right? Because a to the 0th power is equal to 1. Then we'll graph 1, 0. After that, we will look at how the graph is growing. Suppose x becomes less. Then, since the definition is log a of x is equal to x, and essentially this is y at the moment, so when x decreases, a remains the same, so this thing decreases as well. So for a point between 0 and 1, it's going to be located somewhere down here. For a point greater than 1, it is going to be located somewhere over there. So if we connect this, we obtain the graph, which looks somewhat like this. And you might notice this thing, it resembles the exponential function. However, this thing over here is growing quite slow, where the exponential function is exploding. So we call this logarithmic growth. In fact, the harmonic series grows at the speed of logarithmic growth. So many of you might have mistaken that the harmonic series is convergent. So that kind of shows just how slow it is. But it is anyhow still growing. Next, let's consider a is between 0 and 1. That essentially can be treated as 1 over a when a is greater than 1, right? So essentially, if I'm asking log a of x where a is less than 1, we can just graph log 1 over a of x, which is when a is greater than 1. However, this thing is simply negative log a of x. So for the second scenario, we just have to flip it. And when a is between 0 and 1, the thing is decreasing. And that is our logarithmic graph. Now, we have done everything about the definition, the properties, and now it's time we explore some problems. Because after all, we are here to train our problem-solving abilities and, of course, also prepare for AMC12. Since I really understand that learning an entirely new topic can be a little bit challenging. And when I first got into the definition of logarithms, I struggled a lot because sometimes it's just unnatural to think about them. But when we do some practice, it's going to get a lot easier. This is selected from AMC12 2018, problem 7. You can try it, difficulty 2. The way to go here is you try the change of base formula. And surprisingly, everything cancels off except log 3 times log 5 under log 27 times log 5. The reason I'm writing it like this is because you might notice this part is 3, this part is 2, so 3 times 2 is equal to 6, and we are done. The reason that we considered the change of base formula is simply it's a series of multiplication, so it just makes sense to try if we can write it into fractions. Next problem. This is from 20A, problem 14. Difficulty 2 again. Which is the value of a for which the following is equal to 1? Again, we try change of base. Essentially, it's just saying log 1 over log a over log 2 plus 1 over log a over log 3 plus 1 over log a over log 4 is equal to 1, where log is just a general base. Then this is actually simply equal to log a under log 2 plus 3 plus 4, so it's multiplied when we move it into the parentheses, and this is 1. So a is simply 2 times 3 times 4. The answer is 24. Did you get it correct? I hope so. Let's keep on practicing by moving on to the next problem. This is from 2020B, problem 13. I originally gave this a difficulty of 2 again, but I think it's worth 3 actually. It requires a little bit of exploration. Try it out. So I hope the first thing you notice is that 6 is equal to 2 times 3. That means we can try working around inside this thing. Let's just denote this as square root of s. Then s is equal to log 6 over log 2 plus log 6 over log 3. Let's apply product to sum. That means 1 plus log 3 over log 2 plus 1 plus log 2 over log 3 is s. There's a 2 here, so let's write it together. Now what? You probably recognize this as log 2 of 3 plus 1 over log 2 of 3 plus 2. And now you kind of have to inspect the answer choices, or you are exceptionally good at recognizing patterns. Because a pattern I know is x plus 1 over x squared is actually equal to x squared plus 1 over x squared plus 2. This is very common because it is special, since the middle term is actually a constant value. In this case, everything fits perfectly, so this is equal to square root of log 2 of 3 plus square root of log 3 of 2, or this is just 1 over log 2 of 3 squared. So square root of s is in fact b, and we are done. The next problem is not hard, but a little tricky. This is 2014A problem 18, difficulty 2.5. Try it out. And I would really like it if you can do this problem yourself, because this is one of those problems that really is quite tricky. So essentially, we're asking, what is the domain? We know log a of x must have x is greater than 0, otherwise it is not defined. Then in this case, we can analyze the above equation step by step. First, since this part is the input of log base 1/2, this part must be greater than 0. What does that imply? That implies that log 4 of the other part must be 0, so this part here must be greater than 1. Recall that we have this graph of exponential. When it is greater than 0, when f of x is greater than 0, then it must be x must be greater than 1. So this is what we have. And now we have to solve this thing. This thing implies that log 16 of log 1 over 16 of x is between 0 and 14, because it must be the input of a logarithmic function, so it is greater than 0. And also, the expression must be greater than 1. Recall that for it to be greater than 1, it intersects somewhere over here, which happens to be 1/4. You can solve it yourself. We obtain this new equation, and then we apply the same logic again to find log 1 over 16 is between 1 and 2. So x is between 1 over 256 and 1 over 16. So the length of the domain is 15 over 256. Let's see if you got it correct. Now, we're finished trying super easy problems to warm up. Now it's high time we do something challenging and actually practice our problem-solving ability. Advanced problems from now on. First up, 2013b, problem 22. If you can solve this, I think you have a 100% of passing the qualifier of AMC12 so that you can try AIME. We're asked the product of the solutions. So remember, we're solving for x, not log of x, whatever log is, whatever the base is. So the product of the solutions for x, since this thing resembles a quadratic, the highest degree is 2, we can guess there are two roots, then we want x1 times x2. Then that, if we take the log of this guy, we have log x1 plus log x2. So in fact, even though the problem is asking for the product of the solutions, we're actually just looking for the sum of solutions of log of x. Let's keep this in mind and we'll try to solve it next. So the problem is asking for m and n, and whereas the product must be a integer and the smallest possible one. Let's not worry about this constraint first. It is not clear whether we can guess that the answer is a set value like 1 or 2, but rather, let's first try to solve this, okay? Let's just not worry too much and just solve this thing. Applying change of base, we can rewrite the equation as 8 over log n times log n times log x squared, because this is the target variable that we're really trying to solve, minus 7 over log n plus 6 over log n multiplied by log x minus 2013 is equal to 0. This suggests Vieta, of course, because we want the sum of solutions. So the sum of solutions, first we have to convert this into a basic polynomial, and then we apply Vieta. So in this case, the answer is actually, the expression for this thing is actually simply 7 times log of m plus 6 times log of n divided by 8. Great news. Now we have the intimidating task of actually finding when this thing can be, and then since the logarithm symbol is messed up here, let's just move it out. So we want to move it out so that we actually know x1 times x2. This thing can be simplified down to log m to the 7th degree times n to the 6th degree divided by log divided by 8, which is also multiplied by 1 over 8. So the entire expression is actually log 8th root of m to the 7th degree times n to the 6th degree. And now we can remove the log sign because both places have a log sign. Then x1 times x2 is equal to square root of 8th degree root of m 7th and n 6th. We know m and n are integers. First of all, we can assume that in the prime factorization of m and n, it must all be the form 2 to the kth power, because 2 is the smallest prime. And we really want x1 times x2 to be the smallest, so we're taking the smallest possible base. That means 2 to the 7th k times 2 to the 6th k 2th power, this is k1, must under 8th root, that is essentially 2 to 7k1 plus 6k2 divided by 8. Some trial and error will show that k1 must be equal to 2, k2 must be equal to 3. This is the smallest possibility. Then m is equal to 4, n is equal to 8, and the answer is, and we're done. So this is a classic example of one of the key ideas, and possibly, this is what I'm talking about, the most important idea in logarithms, which is converting a product to a sum. And of course, the reason that here we're converting is because in the entire expression, there is log of x, but no x in itself. So really, we want log of x over x itself, because log of x is easier to obtain from this expression. That is the logic behind this problem. And the next problem we'll be tackling is a reason why exponentials and logarithms are so close to each other. And let's just try this together. This one is 2021, problem 21. Try it yourself. I hope that you at first concluded that x equals square root of 2 is a solution from observation. Next, we are trying to verify if there is any more solutions to that. Let's first do it intuitively by analyzing a graph. Now, remember what we did when we were trying to analyze a to the x power equals b. We took the logarithm of each side, like this, so that we successfully moved the exponent out to become a multiple rather than an exponent. So we can try this logic again. In this case, we can take log of 2 on each side, because there is quite a lot of 2's in here. So when we take log of 2 on each side, what we gain is 2 to the square root of 2's power times log 2 of x is equal to 2 to the x degree times log 2 of square root of 2. Or this is simply 1/2. And the right-hand side here can be simplified down further to 2 to the x minus 1 degree. Now, let's take log of 2 again, because there is still exponentials. This time, the first part is square root of 2. The second part, since we're using logarithms, we're turning multiples into addition, then the second part is actually log 2 of x, which is equal to x minus 1. That means log 2 of x is equal to x minus square root of 2 plus 1. And from here, we're a little mystified. We don't really know what to do next. But don't forget, we're studying functions, so there is a really useful tool, which is graphing. Let's try it out. Here's the result. You can see there is a line here that resembles the logarithmic graph, and it is actually taking log 2 of x. It provides an even slower growth. And then after that, we also have the blue line. You can see this point is just square root of 2. That means the second solution is somewhere here. And this looks a little bit more than 3. So we can calculate it, and that means it is by far less than 6. So the answer is this. However, suppose you don't have the Desmos website, because when you're doing the true exam, you can't use Desmos. So what to do? You can graph it yourself. How exactly? First, let's analyze log 2 of x. When is this thing equal to 0? It is when log 2 of x is equal to 1. So that means x is equal to 2. So this graph passes the point 2, 0. And then the next value that we can actually evaluate is x equals 4, because we really do need a multiple, no, an exponent of 2. So when x is equal to 4, it passes through the point 4, 1. And that already gives us a decent understanding of the graph. Of course, you can also check in case we have 1, then log 2 of x is equal to. So we can first graph these 2 points. We have 2, 0 and 4, 1. And we do want to understand what is the domain of log 2 of x. In this case, log 2 of x must be greater than 0, because you can treat the function as this. That means x must be greater than 1. So we can draw the asymptote, and what the asymptote is a line where the function is approaching but is never reaching. In that case, this is a vertical asymptote. Then we can obtain the graph that looks more or less like this. And yeah, of course, the asymptote for the exponential function is the line y equals 0, and the asymptote for the logarithmic function is x equals 0, in case you're wondering. So this is the first graph, log 2 of x, and we now want this. This is really easy. I bet you can plot this yourself. You have to draw the point somewhere down here, which is negative square root of 2 minus 1. And we draw a line. It is quite clear that when x is equal to 4, f of x is already greater than 1, implying that the intersection is somewhere before. So we're done. The answer indeed is D. Did you get it correctly? Now, let's challenge an even more difficult problem. That is very interesting, in my opinion. It is something related with sequences, what we just learned. Let's try it. First, let's read the problem together carefully. We have the operations, and we have the sequence. Apparently we only know A3, which is an interesting design, because we don't know A1, A2, nor A0. And for n is greater or equal to 4, it is already defined. Let's analyze what this actually means. So 3 heart 2 is equal to 3 to the 1 over log 7th of 2th degree, which is a crazy mess. But remember, what did I say we're supposed to do when we see exponentials? We are going to try to reduce them, right? This is a very powerful thing about logarithms, so we're going to reduce them. Then log 7 of 3 heart 2 is equal to log 7 of 3 divided by log 7 of 2. And if you want to change the base here, this is actually just log 2 of 3. But in a way, it is not the essence of the definition. I think, in my opinion, the essence of the definition is actually dividing. Why? Because if we analyze the first equation as well, we take also log 7 of A diamond B, then this is log 7 of A multiplied by log 7 of B. We also have log 7 of 8 A heart B is equal to log 7 of A divided by log 7 of B. So now if we plug this into the recursive definition, we need to take the logarithm of both sides. Log an is equal to log n heart n minus 1 diamond an minus 1. And recall this part. Log of n heart n minus 1 is equal to log n over log n minus 1. So log n heart n minus 1. Now we're treating this as a whole. We can represent it as x. Then log of x diamond an minus 1, this is a diamond, is then equal to log x divided by log an minus 1 is then equal to log x times log an minus 1. We already know what log x is. So that means we can derive the formula log an, where of course everywhere log is referring to log 7. Let's add it in. Log 7 of an is equal to log n of log n minus 1 base 7 times log base 7 of a minus 1. This thing here can be written as a logarithm because of the change of base, but it doesn't truly matter. Why? It is because log base 7 of 2019, A2019, is actually simply equal to log 3 over log 2 times log 4 over log 3, etc., all the way up to log 20 over log 18. So that means log 7 of A2019 is log base 2 of 2019, because the only terms left are these after canceling. And since the original problem asks for the nearest integer, we know 2 to the 11th power is 2048, and the powers of 2 up to, in my opinion, the 16th term, I think you should remember by heart, or you can just be very familiar with them so when you see them, you recognize them. So the answer is approximately 11, and we're done. Phew, hard problem, but I hope you understood the entire idea of reducing exponents. Let's analyze one last problem where there is literally no logarithms mentioned, but it is still exponents, so we still have to reduce them. This again is integer parts, so it means it is not an easy problem. This one is from 2014A, problem 21. And I think this is a hard level 4 problem. Let's analyze it. For every real number x, let floor of x be the greatest integer not exceeding x. We have seen this multiple times. And then we define this function. The set of all numbers x such that x is between this interval. And notice from here, this is not included. So it actually means 1 is less than floor of x, and it is lesser or equal to 2013. And then we're supposed to find the length of those intervals where f of x is lesser or equal to 1. First, you will try this yourself, and I will give you some hints to guide you through it. Let's do it step by step. The first hint is we have already mentioned that when treating with inequalities, we can first analyze when it is equal. So you can first try to solve this. And for simplicity, let's again write this thing as the decimal part of x. So recall the decimal part of x is actually a repeating or cycling function, so it might be easier to deal with. Try to solve this for x. Since we really want to apply the logarithm to this part of the equation, I think it's natural to first do some manipulation, and we will gain the following expression. And then now we can take the logarithm base 2014 to both sides. The result would be the decimal part of x is then equal to log 2014 of floor of x plus 1 divided by floor of x. When we return everything back, we replace this with x minus floor of x, and then we can also replace the equal sign with the lesser or equal to sign. What we will obtain here for x is the critical expression. Floor of x is less than or equal to x. This is given by the definition of floor of x. And then it is also lesser or equal to floor of x plus log 2014 of floor of x plus 1 over floor of x. This thing does not look very clean, but remember, this thing cannot be treated entirely as a variable that is changing alongside x, because essentially we just want this value to range from 1, 2, 3, all the way up to 2013. The sum of their lengths, which can be written as 2013, I equals 1 to 2013, log 2014 of I plus 1 over I, right? And now, the last part of the calculation is down to you. Do it yourself. This thing, remember the product to sum rule. We reverse that sum to product rule. We get this is actually log 2014 of 2014, which is exactly equal to 1. How fascinating. Such a complex function reduced to 1. I really like this problem. It's very elegant and very well constructed as well. The last problem is optional. It is related with sequences and estimation. If you're interested, check the materials down below for the problem and the solution. This problem, just a hint, because it is a difficulty 5 problem and is quite difficult, this problem is not largely related with logarithms. It is mostly related with exponentials, and logarithms are essentially just the last bit. So 2019b problem 22. The last bit of the session is devoted for exponential function. And there's something really interesting about exponential function. So first, we are truly trying to analyze a certain special case. Suppose we have a function f of x, and at any given moment, let's say t, the function f of t at this moment is growing at the rate of f of t. So essentially, the growth rate of the function, or the line tangent to this point of t, must be equal to this function itself. When is it possible to achieve this? So let's just give an example. For instance, assume the function passes through the point 0, 1. Then at this point, f of 0 is equal to 1. So the growth rate at this moment should be 1, right? This is the growth rate. And that means the tangency line over here should be 1. Then that means the true value of that point should lie somewhere above 1, like here. Let's say this point is 1, something. And then this something, since it is greater than 1, that means the growth rate at that point is also greater than 1. So now the tangency line looks more or less like this, but the next point, where x is equal to 2, is forced upwards somewhere over there. That means essentially that graph is looking somewhat like this, which resembles the exponential function. But I guess it's natural to actually justify this by using a more concrete example. Suppose we have the point 0.1 and the point 1.2. So we can guess, in fact, some function of this type must be an exponential function of a certain special base, which we denote as e. Well, the way to imagine this a bit better is suppose you're dealing with compound interest in real life. At first, you have $1, and then in a set period of time, let's just say it's 1 year, you can have a total interest of 100%. What that means is you can enter the money at the start of the year, you have $1, and then at the end, you are going to have $2 because 2 is equal to 1 times 1 plus 100%. Or more generally, you can separate this 100 annual interest to n parts. That means you're going to have an interest rate of 1 plus 1 over n, right? Because this is actually 100% over n, but you can just write it as 1. And you're going to take this interest n times because you separate it into n parts. So essentially, this is a representation of what happens when you compound n times. And by experience, we know that compound interest is higher the more you separate it into 1 year. So essentially, when this thing becomes super big, it occurs when n approaches infinity. And this is when, at every single point, the rate of change is exactly itself. Because at any given moment when you are trying to receive money, suppose at time t, you're going to receive money, then at that moment, the rate your money is growing by 1 plus 1 over n in this case. So this is the formula we came up for compounding n times. Now, suppose at time t, we have money x. Then after one time step, because every time step is 1 over n, then the money has gained by 1 over n times x. This is the money gained. The rate of growth here can be written as the number of money gained divided by the time step. In this case, it is exactly x. So at any given time step t, the growth rate is equal to the exact value at that moment. However, remember, this is discrete because we only have a certain t. But when this thing becomes continuous is when n approaches infinity. Then 1 over n approaches 0, so you have infinitely many time steps. That means this occurs when this happens, it can be written as taking the limit of n to infinity of 1 plus 1 over n to the nth degree. So we can denote this by e. Going one step further, suppose you have a growth rate of 100 per year and compound for t years. Then you can receive the money 1 plus t over n. Because remember, what the numerator here means is the total interest you can gain. There are t years, the annual interest is 100%, so the total interest is exactly t. That means e to the tth degree is exactly this representation. Because remember, This is growing exponentially. Remember, compounding is growing exponentially, so naturally it can be written as e to the t power. This is the definition of the natural base, the exponential function of the natural base. This is our ultimate conclusion. So this is the very, very special function we're talking about, where at every single time step, the rate of change is exactly the value of the function itself. In lesson 15, we'll use the binomial theorem to prove that this is actually also e can be also written as something like this. And this thing, the denominator is by far larger than the harmonic series, so this thing is clearly convergent. That means e is a fixed value. It is not something that is exploding off to infinity. It is a fixed constant. And we know the constant value is 2.718, approximately, of course. And in reality, in AMC12, all you are required to know is e is approximately 2.718, and even that is not generally mentioned. You just really need to recognize the natural logarithm ln and e as a base. Know the approximate value, and there's basically nothing more. Actually, there is the Euler's formula in the future, but it's not truly what we can call something related with exponential functions. So basically, at this point, just remember the value of e, and hopefully you can remember that e to the tth power is a very special function. That is, of course, in the first rate, and that is, of course, not only an exponential function, but something that has a nice relationship with its own growth rate. That's all. By now, we have concluded today's lesson. I hope it isn't too hard. Personally, I think the basic identities are okay. The practice problems are pretty interesting, and the last bit about E is not that easy to understand and very difficult to explain without calculus or limits. So yeah, even if you didn't get this last part clearly, it's okay. In the future, when you learn more stuff, it's just going to pop out to you far more naturally. So lastly, here is the practice problems. This is a relatively easy problem. And this problem is a problem very similar to what we did today. And finally, a very important homework. And this is actually the hidden part about just how important logarithms and exponential functions are. And this is what I'm talking about throughout the lesson. You have probably by this point realized that logarithms, they are a good tool of reducing multiplication to addition. But we're going to go one step further to prove that this is the only function that functions like this. This is going to be your homework. You will try to prove this yourself. There are three statements. Look at them really carefully and try to understand them. Oh, the third statement is over here. And the first two are related with the definition of the functions. And the last one is that you're supposed to prove that this is actually true. In the lesson, we said that by definition, compound interest can be modeled by an exponential function. And also, the right side, by definition, is modeling exactly that. It is an intuitive way of understanding it. However, can you prove this mathematically? By using the fact that e is equal to the limit of n to infinity of 1 plus 1 over n to the nth degree. At this point, you don't really need to care about what this thing means. It just means n is flowing off. You just calculate everything else behind the symbol. Then you just put it there. Just don't care about it, just put it there when you can't simplify the parts behind it. Try to prove the third statement as well. Since this proof homework is interesting and a little challenging, we will actually cover this in class 2 days later when we cover the next topic. So don't miss out, and I will see you then. Don't forget to subscribe and drop a like, because I hope this series is bringing you fun and bringing you knowledge. Bye.